Welcome in this video where we are going to implement the famous Improved Techniques for Training GANs paper and we will focus in the semi-supervised learning part. So let's say you have a data set with a lot of unlabeled data, and let's say you have only 100 labeled data. So in our case, we'll study the MNIST data set and we'll assume we have only 10 labeled data per digit. So in total, we have 100 labeled examples. And if we train a standard classifier to do that, we will get the orange curve. So we'll get only a 70% accuracy, which is not so great. But again, it's only using 100 labeled data. So that's already a good benchmark. But the thing is, if we combine supervised learning with unsupervised learning, so if we use all the remaining training data of this dataset, but without labels, so if we use those data to do some unsupervised learning, and we combine that with the labeled data, so we are doing semi-supervised learning, we combine unsupervised learning, unsupervised learning, we get this blue curve, and we reach more than 90% accuracy with only 100 labeled data. So that's really impressive. And this is useful in many real-life applications because it happens a lot that we have a lot of data. They are cheap to acquire, but labeling them is expensive. So we have a lot of data, but we have only a few of them that are labeled. And therefore, by combining supervised learning and unsupervised learning, we get those results that are really great. There is a more than 20% gain in accuracy. So let's jump directly into the code. So again, as often, we'll use PyTorch, and I'm using other helpers such as NumPy, Matplotlib to plot the results. I'm using Keras, but just to load the data, to load the MNIST dataset, so that you don't have to download them, on a few other helpers to get to generate the data loader. So to start with, we can create the training dataset. So the first thing we do, we load the MNIST dataset from Keras. We normalize the data between 0 and 1. And then we will simulate a dataset where we have only 100 labeled data. So we'll have the training data that are supervised, train X supervised, and train Y supervised. There will be only 100 labeled data. And then there is the remaining of the data, train X unsupervised. So the unsupervised data, and we don't have labels for them. So then we iterate over all the digits. So we have 10 digits. So for all of the digits, we sample. So first we create a mask just to know which digit are, for example, if I is equal to 0, we get all the digits that are equal to 0. And then we sample some of them. So we get n divided by 10. So 10 is 100, the number of labels. Is with 10 digits, we'll take only 10 labels for the digit 0, for example. And therefore, yeah, we have on one side the 10 labeled data, on the other side the remaining for the unsupervised data. And we append them to the training list. And then after that, what we can do is to convert the list to NumPy arrays by using np.concatenate. And therefore, we return the supervised data, the supervised labels, the supervised data, the unsupervised data on the testing sets. Then what we can do is create a Gaussian noise layer. So basically, this is they use that in the Discriminator architecture in the paper. So this is to prevent overfitting. So basically, you just add a bit of noise in your hidden unit. And I need to create this module because it's not present by default in PyTorch. So you can see it's super easy. You just create a Gaussian layer that has some noise intensity that is parameterized by sigma, the standard deviation of the Gaussian distribution. And then if you are training, you add some noise in your data. And if you are not training, you do not add noise. Now that we have this module created, we can jump on to the generator. So the generator is a simple MLP. It takes as input 100 latent dimension and outputs an image. So MNIST data that are 28 by 28 pixels. And we're using soft plus activation function, and we're using batch norm as they do in the paper. Then you can jump on to the discriminator. The architecture is a bit more involved, but it's still using MLPs, so pretty simple. You see that we introduced the Gaussian noise layer that we've created before. We are also using weight normalization. And we are splitting the network in two, so the head and the tail, and I will come to that in a moment. So here you see that what we do, we first get the features after some add some activation functions. And then we get the score, so the discriminator score, and we return both the features and the score. And therefore, why do we do that? Why do we get the features? And therefore, this is why we split the network in two. It's because in the paper, they introduced feature matching loss. So basically, if f of x is the activations on an intermediate layer of the discriminator, so in our case, this is f of x is the output after this network. So this is the activation functions after this value. And then what you do is you will take f of x, so on real data, and you take the difference between f of g of z. So you take the features on real data and the features on fake data, and you take the difference between them. And this is the feature matching loss that is used to train the generator instead of using the score of the discriminator. So now that the discriminator is ready, let's move on to the training loop. So we'll take the generator's input, the discriminator, we'll take an optimizer for each of them. We'll take the supervised data loader, the unsupervised data loader. So in the paper, they create, or in the code, to be more precise, they use two data loader, one for training the generator, one for training the discriminator. Basically, we could just use one. So yeah, that's really up to you. You can use two or just one. It should not change the results. Then the testing set, just to log the testing accuracy over training, and then a few more parameters, such as number of epochs, the size of the latent dimension, a lambda parameter. We'll see in a moment what it does on the device on which we want to train. So we can iterate over the number of epochs with creating a testing accuracy variable to log the testing accuracy over training. We can start by training the discriminator. So first we get our unsupervised data and our supervised data from our data loaders. And we will create some fake data because they are needed for computing the loss. So we can start with the supervised loss. So the supervised loss is super easy. It's just the standard negative log likelihood loss. So our discriminator outputs two values. Okay, so what we are doing, let me double check that. Okay, we are outputting 10 values because we have 10 digits. So basically, at the end of this of training, as opposed to what we usually do, in this case, we will drop the generator and we will only keep the discriminator, because what we wanted to do at the very beginning was to do classification. So we'll use the discriminator to do classification. So our discriminator is a classifier that outputs 10 values for 10 digits. And therefore, the first part, the supervised loss, is super easy. We're just using a supervised training. And if we're not doing semi-supervised learning, we could just stop our code here, line 96, and that would be just simple supervised learning. But now what we want to do is to do some semi-supervised learning. So we want to add the unsupervised loss to make useful use of the unsupervised data. On here it seems a bit complex, but basically if we go in the paper, so what we do, we add one label for the data that have been for the fake data. So the discriminator predicts the value of each label, but we added an extra label that tells if the data is a fake data. But we don't want to modify the architecture of a discriminator on that 11 labels, because after training we have only 10 labels. So what we do, we do a row parameterization that allows to add an extra label without modifying the architecture of the discriminator. And I suggest that you read this part, section 5, in more detail to understand a bit more this function, but it's described in the paper, and we're just doing a row parameterization. So once that we've trained the discriminator, we can combine the two losses. So there is the supervised loss and the unsupervised loss, and we can scale the unsupervised loss by a parameter lambda. In our case, we'll just set it to 1. Now we can move on to training the generator. So we take the unsupervised data, so the real data, we create fake data, and then we can just compute the feature matching loss. So we take the features for the real data, the features for the fake data, and we compute the MSE loss between them. And then we can just do the gradient update. So yeah, quite simple. Training the generator is easy, just the MSE loss between features at different activation functions. The supervised loss for the discriminator is easy, and the unsupervised loss is a bit more involved. but it's well explained in the paper. And then what we can do is to test at every epoch to test the accuracy. Just computing the accuracy. And now we can put all the pieces together, so we can call our function generate training dataset. To generate the dataset, we create our data loaders. Then we can create the generator, the discriminator, and the optimizers. And then we can feed everything to the training loop and train our neural networks. And once this is done, we can plot everything. We can plot the testing accuracy and save the figure. So that's it, in about 100 lines of code, 150 to be precise. I really hope that was helpful to you. If it was, please leave the thumbs up. It really helps with this channel, and subscribe for more videos like that.